Oh, uh, okay. The recording started right now, uh, and well, so we have now subshifts, and given two subshifts, for simplicity, I will discuss subshifts over the same alphabet, but this is not really an issue here. So uh, we have the notion of topological conjugacy. Uh, Two subshifts X and Y uh, contained in A to the Z are conjugated if there exists a homeomorphism phi from mapping one of those subshifts onto another such that uh, this homeomorphism commutes with the shift action restricted to each of those subshifts. So subshifts are subsystems of the full shift system A to the Z sigma. So so now uh, let S of A be the space of all subshifts. Then the topological conjugacy relation on the space of all subshifts. So the space of all pairs XY of subshifts such that X and Y are conjugate. This is actually a equivalence relation on the space of all subshifts. So, uh, so this equivalence relation divides the space of all subshifts into equivalence classes. And of course, if we want to understand all subshifts, uh, then there's a valid question how complicated or hard is to classify uh, elements of the space of all subshifts according to um, the equivalence relation given by E. So this kind of question is one of the many questions we ask across mathematics. We are given a collection of objects. In many occasions, those collections of objects, they do not even form a set. We are given a class of objects, and we are given a notion of isomorphism of those objects, which tells us that according to from a certain point of view, two objects are isomorphic or identical whenever we use our notion. This divides the class of all objects into equivalence classes, which again can be proper classes, and a question is whether we can compare how hard is classify objects according to given equivalence relations in a meaningful way. Okay, because the whole discussion Okay, we have one concrete instance of this problem, which is the classifying shift spaces according to the equivalence relation. And we have also vague or very general notion of classifying mathematical objects according to isomorphism. So, uh, yeah, we have uh, those two. This we consider this particular problem. Okay, so what is here important is that uh, SA is a compact metric space with the topology given by the Hausdorff metric inherited from A to the Z. So A is a finite discrete set. A to the Z is a countable product of discrete metric spaces, finite metric spaces. So that's a compact metrizable. A to the Z is a compact metrizable space. Every compact metrizable space has a natural topology on the space of compact subsets of that metrizable space. And the way we define subshifts is that subshifts are always compact subsets, compact non-empty subsets of the space to the A to the Z. So we can take the induced topology on the space of subshifts. This topology is still induced by the Hausdorff metric, and it is well known that this space is then compact Hausdorff space again. So S to the A uh, is a compact metric space, and therefore the equivalence relation of isomorphism of subshifts is now also a subset of a compact metric space because product of SA with itself is still compact metric. So E turns out to be Borel subset of SA square, and finally, the final observation is that every equivalence class of E is at most countable. So this follows from the well-known uh, uh, Curtis Hedlund-Lindon theorem. So for shift spaces, it is well known that every every isomorphism or topological conjugacy so this is theorem actually, theorem of Curtis Hedlund Lindon. I think those three names are usually associated with that result. Every isomorphism between shift spaces is induced by a block map. So what does it mean? It means the following, that phi between two shift spaces x and y is uh, a shift commuting. Actually, uh, the more precise statement would be phi is a shift commuting continuous map between x, y in the shift space, the two elements of the space of all subshifts, even only if there exists a map capital phi, so there exists a say positive integer n, and there exists a map phi from a to 2n plus 1 to a, uh, such that we have the following picture: for every x equal xi I in z in the capital X, we have the following formula. If I want to see what is in the image of small phi of this map on the point X at the some position K, then I have to take the block of coordinates around position K in X. So those will be coordinates xk plus 1 up to xk plus n, and in the other direction it will be xk minus 1, xk minus n, and apply the map phi, which tells me what happens at the position k in the image. So on the picture we have our sequence x0, x1, x minus 1, etc. And then at some position k, we want to find the value. So we look at the n coordinates in x following xk. So those are xk plus 1 up to xk plus n. We look into k coordinates n coordinates preceding xk in x. This gives us exactly a set of 2n plus 1 coordinates, so elements of A, and to this we apply the map capital phi, and this gives us exactly what we will find in the image of small phi on X at the position K. When we want to see what happens at another position, we slide this window to center it at the position which interests us, and we apply this map. So of course, so sometimes n is called the radius of small phi. So this is how much uh, anticipation and how much memory my block map has to have in order to be computed. This is well, actually this theorem is uh, an easy consequence of uniform continuity and commuting with the shift space and the definition of the topology. But this theorem gives us a very important information. This information is the following: that the set of all maps commuting with the shift and which are continuous between two subshifts can be at most countable, because they are at most countable. The collection of all possible maps capital phi is countable. So because isomorphisms are special kind of shift commuting continuous maps, which in addition are not only shift commuting and continuous but also invertible, then we have this fact that each equivalence class turns out to be at most countable. So we encounter the first example of the equivalence relation we are talking about. So let me recall this that the uh, I will still use uh, okay, z uh, row. So let me state this definition one more time. Sorry. Definition: uh, a topological space Z is Polish, is a Polish space if Z is separable and completely metrizable. So there exists a metric compatible with the topology on Z. There exists a complete metric compatible with the topology on Z. So of course, all compact metric spaces are examples of Polish spaces, but they are more spaces like that. Actually, most of the spaces considered in the usual mathematics to turn out to be Polish. In a sense, that's a prevalent notion. And why we consider Polish spaces? Because for Polish spaces, the theory of Borel sigma algebra is the most regular, behaves in the very regular way. So, uh, oh, so now the next definition will be that an equivalence relation E on Z. So we keep denoting Polish metric space by Z is Borel if E considered as a subset of Z square is a Borel subset of Z to Z. Uh, well, whenever I use products, I will consider products with the product topology. So an equivalence relation is Borel. A countable Borel equivalence relation is a countable, maybe also I can define finite. A Borel equivalence relation is a Borel equivalence relation such that all equivalence classes of relation E, such that all equivalence classes of E are at most countable or finite. So we have this situation that we among all Borel equivalence relations, we distinguish a class of equivalence relations in which all equivalence classes are either countable or finite. So returning to the shift picture, so our main problem for this lecture is that the equivalence relation of isomorphism of on the space of all subshifts is exactly an example of a countable Borel equivalence relation. So now uh, uh, so now what are the other examples of Borel equivalence relations. It is like an example of a finite Borel equivalence relation is identity on a Polish space. So this is a trivial equivalence relation, and it is trivially finite equivalence relation. And another equivalence relation would be the relation which is called E1. Uh, okay, let's call it E1. This is an equivalence relation on the set of all binary sequences. This time I consider only one-sided binary sequences. So two binary sequences are in the relation E1, even only if there exists an index n greater or equal than 0, such that for every m greater or equal than n, I have xm equal ym. So two, two, uh, two sequences are in the relation, even only from some moment on, they are the same. This is E1 is a countable Borel equivalence relation. It can be seen like that, and it is not finite, but E1. So I can define the following finite equivalence relation for each n greater or equal than 0. I define the relation E1 with the upper index n to be the following relation on the same space here. Two sequences of zeros and ones are in the relation E1, even only if for every m greater or equal than this upper index n, I have xm equal ym. So, this is a finite Borel equivalence relation, and one can see that E1 is a countable union of the relation E1's upper index n. This is easy to see. So this is another example of a Borel equivalence relation, and there is another definition on describing such a Borel equivalence relation. A countable Borel equivalence relation E on Z is hyperfinite if there exists a collection, countable collection of uh, finite Borel equivalence relation. Such that our relation E is a union of those finite equivalence relations. So we can carry on this description and introduce more and more notions about Borel equivalence relations. But this does not help us with the question of uh, uh, classifying how complex are two classification problem based on Borel equivalence relation or on equivalence relations on Polish spaces in general. So let me state the main tool used to let me introduce the main tool used to classify Borel this complexity, which is called Borel reduction. Uh, so, uh, well, I assume that the notion of a Borel subset is well understood in my audience, but please, in any moment, if you feel that I should define something because it is helpful to understand the talk and you don't know the definition, that please don't hesitate to interrupt and ask questions. I know that technically that might be hard, but nevertheless, please do not hesitate to interrupt and ask questions. So maybe that's a good moment to ask, are there any questions so far? You know that I see a very dark room, so you can be all sleeping there. You have a nice cinematic audience hall. Okay, so now we have the following. Z and Z prime are Polish spaces, and E prime are equivalence relations, not necessarily Borel, on Z, Z prime, respectively. So we have those two notions, and then we say that Z with the equivalence relation is E is Borel reducible to Z prime E prime if there is a Borel map phi going from Z to Z prime such that for every two elements, small x, small y in Z, we have that x is in the equivalence relation E with y, even only if phi of x is in the equivalence relation E prime with phi of y. So, uh, on the picture, we have the following situation. We have our two spaces, Z int Z prime, and we have a map, small phi, which is Borel, which is a nice map in this sense. And now we have, whenever I pick x and y, 2 points in the space Z, and if I ask a question, if they are in the equivalence relation E, then I can map both of those guys through a map phi to get the points phi of x and phi of y. And assuming that I can answer the question whether those two guys in the equivalence relation E prime, this answer, yes or no, translates back to my original problem. So, in other way of saying that would be that assume you can resolve a question about classification in Z prime, about E prime classification in Z prime. Then we can use phi to answer the question about classification, E classification of Z. So now that is a good moment to answer the following. Is it why we choose Borel as the regularity notion for us? So recall that the sigma algebra of Borel sets is the sigma algebra generated by all open sets in a topological space. And if my space is metrizable and separable, then there's a countable basis of topology. So all open set is an at most countable union of open basic sets. And in a sense, all you need to generate all Borel sets in a given separable metric space is a countable data about uh, the basis of topology, because first you take all countable unions of basic sets, and this creates uh, all open sets. Then you take complement of all open sets and you obtain uh, all closed sets. Then applying the operation of taking countable intersections of open sets and countable unions of closed sets, you will get the next level of Borel sets, which are often called G delta and F sigma sets. And you can continue iteratively this generation of next levels of a hierarchy of Borel sets uh, using transfinite induction and countable operations. So in a vague uh, but I hope well easy to understand manner, all Borel sets in a given Polish space, they turn out to be uh, kind of countably generated by a transfinite induction process starting from a countable collection of open sets. This, in some sense, means that if you allow yourself to algorithms which run for infinitely many steps, but still inductively, so so algorithms which need time counted by a countable ordinal, then all Borel sets are examples of mathematical objects computed by those algorithms. So this is of course not a satisfying notion of computability for uh, theoretical computer scientists, but it's a reasonable notion of computability here. So Borel relations are therefore relations for which uh, they are those countable protocols, countable algorithms allowing us to compute those. And Borel maps are also, in a sense, nicer or more computable. In a very vague way, if something is non-Borel, then in a definition of that object, somehow a quantifier over an uncountable set has to be used in a way making that use of quantifier over non-countable set uh, impossible to remove from the definition. So inherently, the definition of those objects, they uh, of non-Borel objects, they need some kind of uh, of uh, of appearance of this kind of quantifier. So this means that uh, Borel non-Borel distinguishes between mathematical objects with nice description and not nice and harder description. So what would be now the ideal resolution to uh, a classification problem? Okay, so what would be such an ideal resolution? Okay, so ideal resolution to a classification problem will be as follows: that what is an invariant for a numerical invariant? Numerical invariant, sorry. No, numerical invariant for a classification problem given on a Polish metric space Z with the equivalence relation E is a map phi from Z to the real numbers such that we have the following: for every x and y in Z, we have that x is in the equivalence relation with uh, with uh, y, even only if phi of x is equal phi of y. So this is the well-known, I don't know, from mathematical Olympiad notion of invariant used in a more sophisticated, fancy way. Uh, and of course, this is something which is called complete invariant sometimes, not just an invariant. So we have a function, and this function for each object of interest returns a number, and this number determines uniquely the equivalence class of my object. So observe the following: uh, if there exists phi from Z to R, which is Borel, then we have uh, ZE is Borel reducible to the relation. So this is identity on R, right? So uh, we can rephrase the existence of a numerical Borel invariant in terms of our Borel reducibility. Let me also introduce a missing piece of notation here. We write in this situation that ZE is Borel reducible. Maybe I will just use the smaller or equal sign. ZE is Borel reducible to Z prime E prime. So so uh, so now this fact of the existence of a numerical Borel invariant can be described as this way: ZE is Borel reducible to the identity or equality relation on R. And this is, in a sense, an ideal solution. We have the situation in which we start uh, with a problem, classification problem. We find a nice Borel map, so a map which is computable in this transfinite protocol sense, and computing that number, single number, determines whether two objects we have are conjugated or not. So in dynamics, there are two known examples of such a nice uh, ideal solution to the classification problems. If you don't know the details, then don't worry. I don't have time to present details. It is like this is a kind of example for those who know, they will know. Who For those who don't, then you have to dig a little bit deeper to understand why this fits. But there are two results. It's a one is a rotation number for uh, say orientation preserving C2 diffeomorphism on the circle S1. So this is a classical result known to the classical notion of a rotation number. It was introduced by Poincaré. It gives us for a diffeomorphism of the circle, it gives us the average amount of rotation per one iterate of that homeomorphism. And then there is a theorem saying that if this homeomorphism is C2 smooth, then actually the rotation number determines its conjugacy class with respect to the topological conjugacy of two orientation preserving homeomorphisms of the circle. So that's a topological conjugacy of C2 smooth maps. The other ideally resolved problem is for Bernoulli processes in ergodic theory. And then there's Ornstein theorem saying that two Bernoulli processes are measurably isomorphic even only if they have the same entropy. So this example requires a little bit more work to be rephrased as a problem of classifying certain equivalence relation on the Polish space. This is not the usual formulation of that, but it can be argued that this again is a situation in which we have a set or collection of mathematical objects. Those are so Bernoulli measure preserving systems. And we have a single invariant, which is a Borel function. So that given a Bernoulli process, we can theoretically, of course, compute its entropy in a Borel way. And then we find out that two Bernoulli processes are isomorphic even only if they have the same entropy. So those are two examples of situation when classification problems are resolved by finding a single invariant. So such a situation deserves its own name. Um, um, Equivalence relation ZE. Again, that's an equivalence relation on the Polish space is smooth if it is Borel reducible to the identity on the set or on reals. So to this uh, equality relation. So uh, so smooth is in the some sense the best possible. Of course, any equality of on finite set is also Borel reducible uh, to uh, to identity on reals, but okay, from now on, assume that Z is uh, perfect. So there's no isolated points and infinite. So in fact, Z must be uncountable. Uh, and uh, E has infinitely many equivalence classes. So to somehow avoid trivial examples, I will assume those two things. So so now we have this uh, situation that we know something about possible comparison between complexity of classification problems given by Borel equivalence relations. And we have this uh, partial order. So it is not even, sorry, it is not yet a partial order. It's a pre-order because, of course, composition of Borel equivalence relation of Borel maps is Borel. So if we have uh, so the being Borel relation of being Borel reducible is transitive, uh, and we we can define that two equivalence problems or two classification problems are Borel be reducible even only if we have reducibility in each direction. So identifying Borel be reducible equivalence relations, we now have a partial order on complexity of those Borel equivalence relations. So now let me still add some family of examples which comes from group actions. So let uh, gamma be a countable group acting on a compact metric space by Borel automorphisms. So gamma acts on X and each element of gamma, small gamma in capital gamma is a Borel automorphism. So it's uh, a Borel measurable transformation, which uh, has a Borel measurable inverse. So now we can define the equivalence relation. So E gamma is the orbit equivalence relation on X. So this is an equivalence relation on the space X, saying that two elements X and X prime on the space X are orbit equivalent, even only if there exists an element small gamma of capital gamma such that gamma X is equal X prime. So even only if X and X prime belong to the same orbit of the action. So because now gamma is countable, E gamma is a Borel equivalence relation, a countable Borel equivalence relation. And a particular instance of that is the action. Again, let us keep A to be finite set as at the beginning of that lecture. So we can now form the space A to gamma, which is the set of all configurations. So it is nice to think about this in the following way. I take capital gamma and I take a finite set of colors given by the set A. Now, for each element, so the simple picture would be like really the picture for Z would be like this, right? I take Z, so I identify, I draw my favorite presentation of Z as a graph, and then I pick two colors, say yellow and green, and I paint each element of Z using one of those two colors. Then I get a function which goes from Z to the space containing my two colors. I can do the same with any other group. So let me take as another example, let me take the free group generated by two elements. Now, the graph which we now consider is a fractal set. I'm not sure if I will be good in drawing that, but I hope you have seen somewhere that picture already. So now we we again can paint each of the vertices of my graph using one of those two colors. So in this way, we again obtain a function going from the group to my finite set of colors. And now every group acts in the natural way on a to the gamma in the how this action can be described that if I want to see what is the image of so now let take G in gamma and maybe let me describe how I take my X, which is an element like this, and then I take H in gamma, and then I act by H on X, and at the position gamma, I should see what's in the X gamma H. So that's a formula for the action. And you can think about it that you have your coloring of the graph, and using an element of the group, you can translate the whole configuration of colors by exactly applying your element and moving all the colors according to that. This gives us a nice continuous action, and besides, it gives us a nice family of examples of countable Borel equivalence relations. But moreover, it also gives us uh, the following: uh, the universal countable Borel equivalence relation is the equivalence is the orbit equivalence relation of the action of free group on the space of all colorings of the free group using just two colors. So why this is called the universal Borel equivalence relation? Because we have the following theorem. If ZE is a countable Borel equivalence relation, then ZE is Borel reducible to this. Let me introduce some notation. Maybe
Dominik,
I should use this. Oh,
can you
okay.
hear me?
Maybe I will add this O, like orbit equivalence relation.
Yes, yeah.
So
Dominik,
then this is this is now the equivalence relation on 0, 1 to F2
no break.
with the this should be okay. Are there any questions at this moment? Okay.
Actually, we would like to maybe have a 5-minute break.
Okay. Okay. So let us make a break until
Let's say
10:15.
10 past.
Okay.
Yeah.
Okay.
Okay. Okay.
Okay. Quick technical question. What time should I stop? Now it should be in uh, about 40
You
minutes or less.
have 22 minutes, more or less.
Sorry?
You have 22 minutes.
32. Okay. Good. So now, so this allows us to somehow complete the picture. So remember that we assume that our equivalence relations that really are non-trivial in the sense that here is this assumption of non-triviality. So the picture for non-trivial countable Borel equivalence relations is the following. The simplest ones is really equality on R. Now, there is a theorem that the immediate successor of equality on R in the sense of the Bowler reducibility. So if I mean by immediate successor, it means that the equality on R, uh, uh, we have first point is that this for countable Borel equivalence relations, uh, we have this picture, and the second information that is that if Z is non-trivial, then equality or on R Borel reduces to ZE. Now, the third theorem I would like to mention is that we remember that we discussed the relation E1, and I introduced the notion of uh, hyperfinite relation. So here's this definition of the relation E1. This is this is a tail equivalence relation on the space of one-sided sequences. And we discovered that this tail equivalence relation is hyperfinite. And we we see that we have the following. If equality on R, again, for the non-trivial equivalence relation, does not reduces, sorry, if ZE is not smooth, then still the tail equivalence relation Borel reduces to ZE. So it means that the equality on R Borel reduces to tail equivalence relation, but the converse is not true. And every other countable Borel equivalence relation, if it is not smooth, still tail equivalence relation reduces to it. And the picture now is not as clear afterwards, but we have this maximally complicated countable Borel equivalence relation, which is the orbit equivalence relation induced by the shift action on all functions of the free group of generated by two elements on the set of all 0, 1 configurations over the free group. So the full shift or binary full shift over the free group, that's the most complicated one. Uh, the picture inside here is still extremely complicated. It's still extremely complicated, meaning that you can take, so as example, how complicated it can be, it is like there is an order preserving embedding of the set of all subsets of natural numbers partially ordered by the containment relation into the space of countable Borel equivalence relations. Well, space is here. I didn't specify what kind of space we are talking about, but there is a construction which takes a subset of integers and produces of positive integers and produces based on this subset produces a countable Borel equivalence relation, and two countable Borel equivalence relations are uh, Borel reducible even only if they correspond to subsets which are contained one into another. So this is so here we can see as complicated poset as the set of as the poset of partially ordered set of subset of integers embedded here. So this is a very complicated picture. Nevertheless, we have those nice things that we have this maximal and we have those two simplest elements. So now the whole game is the following. You pick your favorite countable Borel equivalence relation, and for us, the favorite countable Borel equivalence relation is the classification of shift spaces according to topological conjugacy. And you try to see how this countable Borel equivalence relation relates to that picture. We have of course more classes of special countable Borel equivalence relations here. For example, we have a class which is called treeable. So let me um, an equivalence relation ZE is treeable if there exists a Borel tree with vertices X, a Borel forest, I'm sorry, with vertices X, such that the trees are connected, are equivalence classes of E. So, of course, how you should understand that, that's the following information, that any equivalence relation is a set of pairs. So any equivalence relation is a set of pairs of points from the space X containing the diagonal. Oh, maybe. Okay, yeah. Let us draw it like that, and we can think about, that's a one way of thinking about equivalence relations, right? The equivalence relations are subsets of the set of all pairs. But we can think also about equivalence relations in the following way. We think about points in the space X as of vertices of some graph, and then pairs of points are edges. So two points X and Y are connected by an edge in the graph, even only if a pair XY or YX, because we deal with equivalence relations, which means that our relation is symmetric. So a pair of points is connected by an edge even only if a pair belongs to E. So now all the usual notions of graph theory may be applied to E uh, considered as a graph. And here we think about E as a graph, and then we ask if there is a spanning forest. So we know that E is an equivalence relation. So E is a collection of complete graphs, meaning that in each equivalence class of an equivalence collection or relation, all vertices are connected one to another. Right? The equivalence relation are graphs in which all vertices are connected one to another. So each equivalence class is a clique, and a spanning tree for a clique is a subgraph which does not contain loops. Okay, we ignore loops attached to each vertex. So those kind of loops, we simply ignore their existence. So now uh, we have those cliques giving us an equivalence relation. This is the green subset is a Borel subset, and then we ask ourselves if there exists a subtrees which give us another Borel graph with the property that the not subtrees but a forest such that each tree in that forest is a subgraph of the clique being an equivalence equivalence class and giving us the spanning tree for that. So that's a treeability connection of uh, of uh, of Borel equivalence relations. So treeable Borel equivalence relations are for sure above uh, hyperfinite Borel equivalence relations. So above this E1, 0, 1, infinity Borel equivalence relation. So now uh, you can what we can do is distinguish various classes of Borel B-reducible countable Borel equivalence relations, and we can try to insert our particular problem about particular instance of a Borel equivalence relation, countable Borel equivalence relation, into that picture, using Borel reducibility or proving that certain Borel reducibility is impossible. So in particular, proving that something is not smooth uh, gives us the following fact. If a countable Borel equivalence relation is not smooth, then there is no Borel numerical invariant for that relation. So if we can prove that certain countable Borel equivalence relation is not smooth, then we can prove that there does not exist a, a set, even a countable set of numerical invariants, which will allow us to classify our objects using, according to the equivalence relation, using that invariant. So this is like the, an impossibility result. But this is a simplest consequence of our countable-Borel equivalence relation being above this line. But even if we know that the relation is not smooth, we can still say much more about how complex it is to classify objects according to our relations using that language. So that's a nice stuff. So now we can let me now mention some answers known for our initial problem. So let's go back to our initial problem. Our initial problem is that we work with subshifts on a finite alphabet, and we want to classify them according to topological conjugacy, which gives us a countable-Borel equivalence relation on the space of all subshifts. Now the question is how this countable-Borel equivalence relation fits into the picture I draw you on this lollipop picture I draw you here. And by the general theory, we know that it is at most as complex as the orbit equivalence relation given by the action of the free group generated by two elements on the space of subshifts, binary subshifts over the free group. And on the other hand, it is at least smooth because, of course, there are uncountably many equivalence classes of conjugate subshifts over non-trivial alphabet. So there's a theorem by John Clemens, which says the following: if we consider the space of all subshifts with the topological conjugacy equivalence relation, then this is Borel B-reducible with the action of the free group with the orbit equivalence relation given by the free group action on the full binary subshift over the free group. So the topological conjugacy here is maximally complex. But this does not end the whole story because you can ask the following question. How about some other equivalence classes? So how about minimal subshifts? So how about the class of all elements of the space of subshifts such that for every x in X, the orbit of X is the whole subshift? Or how about transitive subshifts? So that's a collection of all subshifts such that there exists a point X in X with the dense orbit. Well, I should maybe assume something more to avoid some trivial counter examples. But let us for a moment work with this. Minimal is okay. Transitive, maybe it would be better to define it slightly different, but still okay. Because the point is that the way Clemens proved his theorem is that he used subshifts which are uh, in some sense dynamically very simple. So Clemens' theorem tells us about topological conjugacy on the space or on all subshifts, but it is not satisfying for people working in symbolic dynamics because um, the complexity in the Clemens proof, which is of course ingenious, and that's the very first step to do any reasonable stuff. But the complexity comes from the complexity of the variety of the collection of all subshifts, not from the dynamics. So simply we have in some sense uh, you can say that the complexity comes there from the point of view that there are many different conjugacy classes of many different subshifts which are not conjugated for trivial reasons, but dynamics on each of these subshifts on this variety um, is very simple. They are they mostly consist of periodic points, and neither of those shifts carries non-trivial dynamics. So very little. So about those two, uh, I'm not going to tell you about this, but this is seems to be very interesting and hard problem to classify minimal subshifts up to topological conjugacy. Let me just mention here that the best result so far are due to Marcin Sabok and Todor Tsankov, and another results come from Burak Kaya, and there are also some interesting results due to Konrad Deka and Bo Peng about this. I would like to talk about another uh, class of examples which are subshift with specification. So Rufus Bowen, a prominent mathematician in the dynamical system community, kept a notebook with problems, open problems he would like to solve, or some questions he found out interesting, and this notebook is available online, so you can look for more problems. But there's a problem on the number 32 on that list, and it says classify shift spaces with specification. So what is a specification for a shift space? So every shift space over an alphabet A has its language. The language of a shift space is the collection of all finite sequences, words appearing in elements of that shift space. So when a word appears, so let me recall that the word W1 up to W capital L, N appears in a subshift if we can find an element of that subshift, so a B-infinite sequence of symbols, such that if I start looking at symbols appearing from some position on. So I look at some n consecutive symbols, then I see exactly my word W appearing there. So now language is now the collection of all possible words which I can see in all possible infinite sequences in my subshift. Now, of course, knowing that some words are in the language does not guarantee that any arbitrary concatenation of those words still appear in the subshift. So a property of words from the language being able to the possible combinations of words in the subshifts. Sorry, the possible combinations of words from the language, which of those possible combinations appear again in the language of the subshift, is a property of the subshift. So maybe it is better to give some example. So a shift space is transitive if and only if, that's the definition which maybe I wanted to state, even only if for every U and V two words in the language, there exists a third word W in the language. This word is now in the language of the full shift, such that UWV belongs in the language. So transitivity tells you that if you have words you can find in some points in the if you have two words which you can find somewhere in two different sequences in your subshift, then you are able to find those two words together appearing one after another, maybe with some gap, in a single sequence. So there's this gluing word W and a single sequence which allows you to combine those two words together. So that's a condition of transitivity for the subshift. And now specification is a special kind of transitivity which tells you that this gluing word W has a uniform length independent of the words U and V we are going to glue. So let me maybe state this definition. And so the subshift has the specification property if there exists a single length k greater or equal than 0, such that for every two words in the language of my subshift, there exists a word over the same alphabet we are considering here of length exactly k, such that UWV belongs again to the language. So there exists a single length such that for each pair of words, I can find a new word of length exactly k, which I can put between my two words, and I see the concatenation of all three words appearing again somewhere in some point in the subshift. Of course, what are the examples of the subshifts with the specification property? Of course, the full shift is an example, but there is also golden mean shift in what is this this shift? It is a shift in which so this is a subshift of the binary full shift. And the defining property is X belongs to this golden mean shift.
Dominik,
Yes.
we should slowly wrap up. We're already a bit over time. Of course, we were a bit slow to start too, but yeah.
Okay. No problem. So let me just finish the example and I will wrap up. Okay. So golden mean shift is a shift in which a point belongs to the golden mean, even only if no 1 appears in X. And then you can think about why, okay, this condition defines a subshift, but why this subshift has a specification can be an exercise. So I will stop here. Hope to meet you on Thursday.